IoT or Internet of Things, I think you're all familiar with. The two aspects that are really being differentiated as is either consumer IoT or industrial IoT. And that's essentially how Fabric looks at it. Our focus has primarily been on the industrial IoT. That's where we're looking to form companies. We have 2 companies. And within industrial IoT, we break it down further and segment it into 2. The IT side of IoT and the OT side of IoT. So for us, IoT is IT plus OT. Okay. And as we start looking at things, as we start looking at what's driving it, be it your home security systems or your Nest doorbells in the consumer space, or you start looking at the industrial aspect of things, one of the things that is missing is security. The Mirai virus attack on cameras exposed that a lot of the devices that are today being used in the industrial systems or even at homes are susceptible to attacks. So what we've chosen today is we've actually looked at IoT security as the focus area. And I'm really pleased to have experts in the field, 4 experts. So I'm not an expert. We have Ben Hendrick. Ben, please join us on stage. Ben most recently was with IBM, and I'll let the team do the introduction. We have Rajive Joshi, who's with RTI. We have Josh Nash with Microsoft. And we want to make sure what's happening in academia. So we want to make sure that Dr. Rising was here with us. How I'd like to run the panel is essentially let you guys introduce yourself. We have the mics over here. I'll just turn them down off to you. A couple of mics actually standing here. So let's see. On and on. There you go. Just pass some mics down. Why don't we start with you guys introducing yourself and maybe talking a little bit about your areas of interest.
Sure. So my name is Ben Hendrick. I'm a cybersecurity partner focused in the areas of cybersecurity around infrastructure, cloud, endpoint security, which covers IoT. So I've been working in this space for the last 5 years, worked with some very large clients at my previous employer, and I'm getting close to joining a new company here in the next few weeks, but I'm excited to be part of this panel and the opportunity to discuss this topic with you today.
Hi, everyone. My name is Rajive Joshi. I work for RealTime Innovations, or RTI. I'm the principal solution architect there. I've been working in the field of industrial IoT probably for before it was called industrial IoT. We used to call it big, weird stuff. But now we have a name, so it's great. And my focus area is really autonomous distributed real-time computing. So that's really what I've been doing for the last 20 years or more. Come from a robotics background. And of late, my focus has been on autonomous driving and connected cars. And I've been part of our product team as well, building our product stack, which is based on a standard called Data Distribution Service, or DDS. Some of you may have heard of it. It's a connectivity framework. I've also been leading some of the task groups at the Industrial Internet Consortium, the IIC. So I chair the connectivity task group and led the development of the Industrial Internet Connectivity Framework. And I don't know if you guys have seen it, but if you go to the IIC site, you can download it from there. It's available as a no-cost. All the IIC publications are available that way. And then earlier this year, we spun off a task group on automotive. So I'm chairing that as well. So we are ramping up our efforts in bringing together sort of a focus on automotive vertical, in particular autonomous driving and intelligent transportation systems. So that's kind of a little bit of my background. I'll pass on to Josh.
Hi, everybody. My name is Josh Nash. I'm a principal product planner on the Azure Sphere team at Microsoft. Who here has heard of Azure Sphere? Not just Azure, but Azure Sphere. A couple of people around there. I'll get into that in a little bit. But in that role, what Azure Sphere is trying to do is help secure the endpoints, looking to solve the problems like Mirai and what they present in trying to help drive a microcontroller-based solution that can actually have security that is renewable, such that a device can not only be secured at the time of its launch, but actually have the capability to report errors back to a service and be able to renew the security in the form of patching over time. And so we're just coming to market. We've just announced our public preview last week and are working to work with OEMs and anyone in the ecosystem to try to bring products to market on our platform.
Hi, I'm Don Rising from the University of Tennessee in Chattanooga. I'm a professor of electrical engineering. My research is mostly in trusted networking. The research I do is at the physical layer. So the easiest way I can explain it to everybody is everybody has in their pockets, probably right now, driver's license or other ways of you identifying yourself, social security number, birth certificate, et cetera. In the networking world, we would call those digital credentials, right? And those would be like username, passwords, and other techniques of security. But those can be falsified, right? I can get a fake ID when I'm 18 so I can try to buy alcohol, right? So I can have a fun time on Friday night. But what fundamentally identifies you as you is physical traits, right? So that could be physical appearance, that could be your fingerprints, that can be retinal scans. So what I do is my research is focused on kind of the idea of biometrics, using physical features in the actual devices to augment digital credentials in the network so that you can have trust between networked devices. And where does that apply to IoT? IoT fundamentally doesn't use, a lot of devices don't use any form of security, or they have very weak security due to the endpoints just not having computational power, plus who wants to put a very strong encryption key on a device that's located out in some extreme place that it's going to either be lost, destroyed, or possibly easily stolen, right? So,
Good. We have some seats here, so if you guys want to maybe move over here, there are a couple of empty chairs. Feel free to move in. Dr. Rising, when I was speaking with you, you had an analogy on security with respect to like moats and walls of pillar and of castles. You want to maybe elaborate on that?
yeah, because electrical engineering is complex, I like using analogies a lot. It helps my students to understand complex concepts. So in terms of physical layer security, I equate that to you take a medieval castle. You have the gate, the wall, the moat. Think of those as the physical layer. You want to stop the enemy before they get in your castle. Right now, networks don't really leverage physical layer security. They do higher layer security. They use encryption. They use username, password credentials, and other techniques. But those are already letting the invaders into the walls. So why would you want to deal with the network invader when they're already inside your castle? So the way of looking at physical layer security is let's take advantage of those. Let's close the gate. Let's use the walls. Let's use the moat to help minimize and make the attackers work that much harder before they compromise the network.
Great. So that leads us to Josh. So Josh, Azure Sphere.
Yes.
What's Azure Sphere doing with respect to moats and walls?
So around 2015, actually, my boss had somebody walk into his office and show him the schematic of a microcontroller that was, I think it was proposed to be used in a Microsoft product. And what he noticed about this microcontroller was that it had typical things that you'd see in a traditional microcontroller, like a little bit of compute power, some RAM, some storage. But the thing that was unique about it was that it had a radio inside the same die. And what it didn't have, as I think we've caught on as the theme here, is it really didn't have anything about it that was security focused. It had been a traditional microcontroller that all of a sudden you put a radio inside the die, 4 lines of code later, and you have a connected microcontroller. What we looked to do was put some security in place. And so what Microsoft Research did was undertook writing a white paper that was called The 7 Properties of Highly Secure Devices. What we essentially did with that white paper was set a minimum bar of what a device security needs to be in order for it to be a secure connected device. And actually I say secure, but I mean secured. When we talk about secured devices, they're basically secure at the present for all known vulnerabilities, past until the present. And what we aim to do, actually, we use that moat and castle kind of analogy a lot as well, is that we can't expect that nobody is going to get in. And I can't remember the castle that we have the drawing of that's in the UK that has over the years had additional walls and perimeters added to it, because every time somebody breaks into the wall, they think about how can we fortify next time. And the reality is that you can't just keep somebody out, because somebody who's determined enough, who's putting enough resources behind breaking in, will be successful eventually. And so what we needed to do when we were defining what a secure device is to be able to enable that device not only to be connected securely, but also to be able to be renewable, so that the security model of the device can be updated over time to account for trends over time. So bringing Microsoft's capabilities around security that we've been operating under in the Windows world and in the server world, taking that down to low-cost devices that are running on microcontrollers like this.
Great, thank you. Now, what happens if somebody actually is able to break and go over the fence, right? And then does he get free access? So Rajiv, you said to me endpoint security is not enough. You said to me that just securing the pipe is not going to cut it. You've got to secure data. Want to elaborate on that?
Absolutely. Yeah, so I'll build on the analogy that I think you've started, and I think it's a great analogy. So now you've got your castle and things are protected, right? Because nobody can enter with this moat and all the protection you put on it. So that's great. But then, the assets are really the data in the system, right? And not all assets have the same value. That's number one. And number two, how do you move these assets out of this castle to maybe move them to a different castle? That might be another cloud environment, that may be another device, another edge. So how do you protect data in motion, right? So that's really the problem. We are looking at that sort of our background of what we do at RTI and with the connectivity work. So if you look now at the connectivity stack, for example, the IoT connectivity stack, and you see many of you are probably familiar with the 7-layer model and so on, but I'll break it down into 3 simple layers. There's the network layer, which is really the IP infrastructure that we all talk about. Let's go to the next layer. There's the transport layer. People talk about UDP or TCP. Some of you may have heard of those. Above that is the framework layer, and that's basically the layer that's about data. So the transport layer is about securing the messages, which is saying, everything that I'm going to move from this castle to another castle or another place is going to be in this vehicle. And this vehicle is somehow protected, but every asset inside this, every piece of data is at the same level of protection, right? And has the same level of access and same level of authentication. And again, I'm throwing them security terms, but essentially you have no ability to differentiate between one type of data versus another, right? So that's securing the pipe. You're just securing the vehicle. But now what about if you have different classes of assets and different kinds of data? How do you protect that? So that's where the framework level protection or protection around data comes in, right? So you want to make sure that, for example, if you have high-frequency sensor data, and you don't care about making it confidential, but you want to make sure that it has integrity, you can put protection for just signing the messages or that data, but not necessarily encrypting it. So you're saving on the cost there. But then you might have command data, and you want to make sure that nobody can see it, and it's confidential, so you encrypt that. But that's low frequency data usually in these type of systems. So that would be an example of that. The next question is who has access, right? Can I access, if I can get into this wagon that I'm using to move the data out of the castle or into the castle, if somebody gets access to it, do they get access to all the data, or do they have some kind of access control? Only people with the right keys can open certain vaults, right? And then can access certain data items. So that's access control and so on. What about then in the networking world, we talk about multicast. So if you have high volume data and you want to send it to a lot of parties simultaneously, you can leverage multicast. But how do you do that securely, right? So there's another aspect. Right, so all these aspects come into play, and it's really about protecting the data. So that's what I meant by protecting the data, not the pipe. And there are framework level standards. There's the DDS standard, which is data distribution services managed by the Object Management Group, and that standard actually provides you that fine-grained security for protecting the data. So that's
Okay, great, thanks. So we have the moat protected, we have the walls protected, we have the building protected, and we have the data protected. Is my house still secure? Ben?
Well, that in terms of security around what we describe, I think the first question to ask is what are we working with, right? And I remember working with a client. There was a global client that had 600 manufacturing sites around the world that were running on operational technology. And when we asked the question in the workshop as a consultant, what was their security? Their security was it was air-gapped. Air-gap was the answer. But the challenge that we see in today's world is that air gap being the solution is not going to be the solution going forward, right? We know there's going to be a convergence of the IT and the OT worlds, and there has to be defined ways and methods in order to bring these systems online without using the legacy of air gap to be the solution for security. As you break those down, from my area of expertise is around the infrastructure, the networking. Do you have network segmentation in place? Do you have the right capabilities? A lot of these legacy systems, security wasn't even invented when they were created, right? A lot of these SCADA systems are out there, don't even understand what security means. So there's a lot of work that has to be done from our side on the consultants, looking at doing the workshops, the evaluations, looking at what those requirements are. We like to talk about that the day of perimeters and moats are over. It's a perimeter environment now. We find cloud, we find all these disparate, with 5G bringing the new technologies, that trying to get a moat or trying to get a fence around what you're doing is impossible. It's more important to start looking at micro-segmentations and nano-segmentations of how you contain the islands that you need and how that connectivity provides secure transport of the data throughout the environment.
Thanks. So Dr. Rising, can you share a little bit about the research you're doing with respect to fingerprinting in some of the areas to secure buildings? And where do you see it heading from a technology standpoint at the research level?
Yeah, so most of my research is what we call radio frequency fingerprinting. It's just like I said earlier in terms of biometrics. Devices, when we manufacture devices, they're built to a spec. And there's always give and take because we're human beings and we can't make anything perfect, right? There's imperfections in the molds, there's imperfections in the actual process itself, and we account for that. So for instance, we build a radio, it has a local oscillator in it, it's designed to operate, say, at 2.4 gigahertz. Well, when you manufacture a few gabillion of them, they're not gonna be all at 2.4 gigahertz. They're gonna be plus or minus some tolerance, right? And those create imperfections in the actual radio itself. So I'm talking about wireless devices here because most IoT are using wireless, whether that's Bluetooth, Wi-Fi, whatever. And what happens is you get kind of a cascade effect. And these radios, when they transmit, they unintentionally, because of these imperfections in the components that make up the radio itself, change and color the waveform. And so they make it, the idea is that it's unique, just like your fingerprint is unique to you. It's not a way of saying it's the only way of doing security. It's a way of, you can think of it more as a way of creating trust between devices, right? In wireless transmission, you're transmitting from you to somebody else, right? You don't see the other person, the other device you're transmitting to. And the device that's receiving it just accepts in faith that the device that sent it is who it says it is. So wouldn't it be nice to have a way of quantifying and determining if that person is actually valid, right? So that's where our fingerprint comes in. Some of the challenges that come in this is in terms of community of scale. A lot of the research that's been around for about 15, 20 years, it's mostly been proof of concept stuff. So they've done with just a few devices and most of the in offline modeling and simulation. No one's really tried to integrate this into an operational network. And so what we're doing here, we're looking to do at the University of Tennessee in Chattanooga is integrate this into a building that's using IoT, has wireless networks in it, and we're looking at how it would scale when you get 100 devices, 500 devices, 1,000 devices, 10,000 devices. Is it possible, right? And is that necessary? And what's the trade-off at the physical layer with our fingerprinting in terms of performance versus other security mechanisms at higher levels of the stack? We're not, our fingerprinting is a way of enhancing security, not eliminating the need for other security mechanisms, right? So that's kind of the way we're going forward with the research.
Thank you. Rajiv, when it comes to IoT and when you really look at, okay, there's new technology, but there's also existing infrastructure, right? And then there's also a need for interoperability, right? I don't want to delve into all the aspects, but one of the areas that seem to be a concern for me is how will connected cars coming from different manufacturers be able to communicate securely, and we don't end up in a situation where we have major traffic jams and fender benders. So that drives the need for standardization, as well as support between legacy systems and new systems. What is happening in the standard bodies with respect to that?
Absolutely. So there's a number of different things emerging. I can maybe reference some of the work going on at the Industrial Internet Consortium of the IIC. Through the various technical guidance document, there's the reference architecture, there's the connectivity framework, and the security framework. So those are sort of the major documents that have been put out there. The standards being built, but you need standards for communication, and you need to raise the level at which the standards operate for communications. Sure. So one of the minimum requirements that has been identified when you start taking the humans out of the loop and you start bringing autonomy, because these are machines making decisions, is you need to be able to understand the data unambiguously. And that's called syntactic interoperability. Where people are with respect to web technologies are typically syntactic, just technical interoperability, which really means that you and I, we understand each other's language, but if a third party wants to participate, they need to understand our vocabulary and the language and everything else. It's not an open format that's discoverable and anybody can participate, right? It's like my kids make up their own language when they want to have their private conversation. It's kind of like that, right? So you have to be part of that. But then if you go up to the level of the frameworks, like for example DDS, which is an open standard, then you get data in a form that's discoverable. You understand what the syntax is. You still need sort of higher levels like semantics, but then that starts to become domain specific. So there are standards out there for syntactic interoperability out there, and the first thing is that people need to have more awareness, because that's sort of the minimum requirement, and we've established at the IIC. Then the next layer is sort of semantics, and there are standards and sort of efforts emerging in different verticals, and so that is happening also in the automotive space. The automotive space is moving pretty fast. So we are seeing, for example, there's the AutoSAR, which is a collaboration of automotive OEMs, all the big names that you're familiar with, including US, German, and Japanese. They have, there's a new framework that's coming out, or it's been in development for a number of years, called AutoSAR Adaptive. So that's now, earlier this year, as of the 1803 release, that was March, has adopted DDS as a connectivity framework. So they're starting to adopt sort of this type of guidance where, okay, we are going to have that minimum level of interop as well. There's ROS2, which some of you may have seen, very popular with research projects. That's also adopting DDS, so it's moving up the stack as well. And then, of course, we are seeing a lot of startups, especially in Silicon Valley, using that higher level framework with DDS, which is an open standard. So that's one piece of it. There's security specifications around that that come into play. So you need essentially secure connectivity that is at the level of syntactic interoperability, so that your data is discoverable and machines can make autonomous decisions.
Thank you. Ben, you mentioned about IT and OT and the challenges that you saw and what people are talking about. Oh, all we're doing is air gap. But those air gaps are disappearing. So from your vantage point, if there are entrepreneurs over here that are looking to do something in the IoT security space, what are some of the views or some of the problem areas that you would want to have them look at?
Sure. And I think one of the areas that I focused in heavily was oil and gas. So I attended a conference in Houston, and you look at the opportunity to develop new solutions for oil and gas, from the wells, the drills, to the architecture that surrounds it. Most of those systems weren't really designed to have heavy security. Security it was an afterthought. It wasn't part of the integration that occurred. And because those air gaps are going away, there's connectivity now through 5G that we learned about today. The other systems that bring capabilities, there's a whole lot of area of innovation that's going to occur, specifically like in that vertical around oil and gas. So the opportunity to start learning some of those use cases, understanding what some of those problems that they're trying to solve for those various remote locations becomes a great opportunity for entrepreneurs looking to solve some of those business cases and presenting security solutions for them. And I think the type of audience that they listen to, they're more keen today to listen to startups and develop and partner and work with startups if the technology helps provide security solutions that meets their specific industry needs.
Thank you, Ben. And I got a lot of questions for the team, but now the audio outside has gotten louder than me, which means that we're running short on time and people are ready for the party. So with that, if you can just share small parting words for the team, and then we can just call it a day. Starting with you, Ben.
I'll just say one thing I think is important is regulation is coming. How many of you guys have heard of State Bill 327, right? It was just signed. And it brings now requirements by the year 2020 in California that you have to have security and take more advanced methods for devices. So I think regulators are coming at the state level. We know there's regulation happening at the federal level. That will force compliance even down to the consumer level and the operational. So I think that'll help drive the innovation opportunity to provide solutions in that space. And I look forward to the opportunity to be able to play in that space with you all as we develop those type of solutions.
Thank you. Rajive?
Yeah, so I'll just say two things. One is, think about the data and move up the connectivity stack to the framework layer, and you'll see that described in the IICF documents. And when you do that, you can leverage open standards like DDS and security around data with a standard like DDS. And that opens up a whole new world for creating autonomy in a secure, reliable, distributed, scalable, fault-tolerant fashion.
Thank you. It's Josh.
So as you look to use or build devices that are connected, being part of this next wave of computing, I encourage you to take a look at the 7 Properties paper and use it as a yardstick to examine devices that you're thinking about building on top of or thinking about using. I'd encourage you to particularly look at things like a hardware root of trust to make sure that a device has some sort of unforgeable capability to identify itself and to represent itself, and that it's running the right software. When I think about a device, it has a job to do and it shouldn't be doing other jobs. In Mirai, cameras got taken over and got turned into other devices. They should be communicating with the intended recipient of messaging back and forth. In Mirai, they were communicating just with the internet backbone and mounting a DDoS attack. And they should be using an approved message format for that handshake that should be part of an interface agreement. If a device is doing not the job it's supposed to be doing, or communicating with unintended sources, or communicating in message formats that might put the destination system at risk, you've got a problem that you need to look at. And looking at devices that can implement the 7 properties, Azure Sphere being one that can do that at the microcontroller level, you can build a device that not only can be secure by compartmentalizing and segregating vulnerabilities and being able to push the attacker back out and restoring device security, but really can help be renewable into the future so that unknown vulnerabilities today can be accounted for into the future.
Thank you. Dr. Risen, parting thoughts?
I think, one thing that I think we all kind of are aware of is 100% security means zero functionality, right? Sure. So security is about risk mitigation and risk trade-off, right? What's acceptable, what's not. And the key is that we think about from the ground up of incorporating its security. I've heard a lot of panelists say that, this was designed with no security in mind. We have to have IoT devices that are built from fundamentally with security in mind if we're going to truly integrate security, right? It's hard to band-aid something after it's already operational and down the road, right? So we have to look at leveraging different layers and different areas and different aspects of security. So I talked about physical layer security, but that's just one small piece. It's fundamentally from the beginning, all the way from what Josh is talking about with the chip itself and how it's designed with security in mind, to software that's running on that chip and how it's designed with security in mind, so that we strike a balance that gives agility and functionality, but still minimizes our risk.
Thank you. Please join me in thanking the panelists here. And thank you very much.